Meeting is being recorded.
I love being recorded.
Whether or not we can.
And can everybody hear online?
Yes, we can hear you. There are
Great.
some people still unmuted, though.
Ah, could you kindly mute, or can we mute them? So, good afternoon, welcome, thank you for coming. Derek Jones, our speaker, used to write compilers and then moved into static analysis to try and work out what they meant to write. And I asked him, didn't they know what they meant to write? And he explained that no, sometimes they didn't. They'd write something which was going to produce, when compiled, a completely different result from that which they intended. And now he does evidence-based research in software engineering. And I asked him, what other kind of research is there? And he said, you'd be surprised, a lot of it's about opinion. Anyway, Derek's going to talk about the relative performance of over 1,000 computers, which were launched between 1953 and 1993. But he's only got about 45 minutes to talk, so he's going to have to speak very fast. I have to say, personally, this is a fascinating topic for me, because when I joined Logica in 1972, I joined the computer performance analysis team, and we would go around mainly government computers, but also private ones, measuring the performance, predicting what it was going to be when they installed a drum or whatever they were going to do, whether they needed a drum, and the CCA always said, no, they don't, no. But we said, yes, they did. Anyway, so a topic of great interest for me, and I'll hand over to Derek.
Thank you, Chris. Okay, yep, good. So there's me. So just quickly covering what the intro already said. If you want to find me, you can find me in these various places. The slides for this talk are online. If you go to my GitHub repo, you can find them all there. So there's lots of references here. So if you can take pictures or go there. I have a blog called The Shape of Code, where I analyze and talk about things. I have a book, and you can go and download the PDF. This is one of the few printed versions available. There are about 20 versions printed. Because the PDF is free, I've had about 500,000 downloads of the PDF and sold about sort of 30 or 40 copies of the book. But it's out of sale now. So yes. So onto the talk. So I'm going to be talking about different methods of estimating. How do you estimate the performance of computers? I'm going to talk about two particular data sets, two very good data sets, and then talk about how we can align those two data sets to come up with a number to cover the entire period. So I do tend to rattle along, and I'm definitely going to finish in less than 45 minutes unless people ask me questions. So please ask some questions. So what do we mean about performance? What are we measuring? And all these estimates that I'm going to be talking about, they're single CPU, not vector processors, not multiprocessors. It's all single CPU. Minimal I/O, so it's very much a CPU-orientated measure of performance, which is not necessarily what people want. I imagine you found that people were more interested in throughput or wall time than CPU time. But of course, CPU time is much easier to measure. So that's what people measure. And it produces a single number. Some metrics produce more than a single number, but you do get a single number. And there are two ways have been used to measure performance. In the early days, they would look at the CPU and they would say, well, how long does it take to do an add, multiply, whatever? And they look at the characteristics of the machine. And there's a guy called Kenneth Knight, his PhD, did all this work. I'm going to be talking a lot about him. And the other way of measuring computer performance is to use a benchmark, take a program, representative program, and then run that on the computer and see how long it takes. So we have the whetstone benchmark, then the drystone, and then these days we have the SPEC benchmark. So two different ways, one by analyzing the computer and do some theoretical analysis, and one by running real programs. So talking about the characteristics of the machine. So Kenneth Knight, his PhD thesis in 1963, he kicked the whole field off. He produced a huge amount of data. His thesis was actually 225 computers, and then he did a follow-up. Underneath, you'll see the links to his work in datamation. In the early, up until about sort of 1985, 1990s, magazines used to publish data. You would have pages of numbers in the magazine where they would publish the figures for the results. And datamation actually published, they've got pages of numbers, which is where these numbers come from, published figures. There was also another study in the early 80s where they were measuring things like how much cache memory, the clock rate, and that sort of thing. Yes, it's one of the problems with measuring a number of operations per second is what is a representative sample? It's all very well saying an add takes this long and a multiply takes that long. What you want to do is find out in real programs, how many adds does a real program do? How many multiplies does a real program do? You want to weight the instruction execution time by the likelihood that that instruction will be executed. And this approach also assumes that the instruction execution times are constant. And as we will see, instruction execution times are not constant, but it's an assumption that gets made. And it also assumes, which is true in the early computers, that there's one instruction per arithmetical or logical operation. For instance, if we're going to do an add, you'd think, oh, I'll go and look up the instruction manual for the computer. What's the add instruction? Now, on the early computers, there was only one add instruction. Now, if you go and look at the Intel instruction set, you'll find there's probably about a dozen different add instructions. And so what actual add instruction timing should you use? So when you're doing an analysis based on machine characteristics, you've got to assume, first of all, that the instruction time is constant. You've got to assume that there is essentially one instruction performing one operation, or you're kind of getting into trouble. And also, you're going to need a representative sample of programs. And in Knight's work, he had a representative sample of scientific programs, and he had a representative sample of commercial programs. I imagine people here remember back in the day when people were always talking about scientific computers and commercial computers, or you're doing scientific workloads or commercial workloads, and the two were different. And if you look at the instruction mixes, they are different. So you have to weight things differently. So this is an example. People were doing surveys, organizations were doing surveys. Sorry about the size, this is a screenshot. So in 1953 rather, the Office of Naval Research did a survey of computers and published it. You can go on archive or search the web and you'll see this survey of about 100 different computers. And you'll see things like, here is the time to do an add, the minimum time, the maximum time, multiplication, division, and so on. So this is from 53. The Ballistic Research Laboratory in the Aberdeen Proving Ground, they published surveys in the late 50s and early 60s. And so they have a lot of this kind of detailed information about the size of the machine, who it's from, who built it, 41 binary digits and all sorts of other details about the machine. So this data was readily available in Knight when Knight did his thesis in 63. And in fact, now, because of the internet and people scanning in documents, it's suddenly become available again as of the last 10, 20 years or so, which is fantastic. So how did, this is Knight's formula here. He calculates the weighted measure of number. You look at how long does it take to do an add, and he has a weight for the add, how long to do a multiply, and so on. These are the weights for the scientific computers. These are the weights for the commercial computers on the right. And so to estimate the performance of the computer, you'd look up how long did it take to do an add, how long did it take to multiply, divide, and so on. And you plug them into this formula, and then he'd give you a performance number. That's how he did it. The surprising thing is that the performance figure also includes the amount of memory on the computer, which is somewhat surprising. Memory goes into performance. But you can see back in the day when memory was at most a few kilobytes, if you didn't have much memory, you'd have to swap out to disk or whatever when swapping became available, and that would slow you down. So that was his formula. As I say, he's assuming that you plug in the numbers, that there are different ways of doing the instruction. The cycle time of the memory was very important as well for performance. So it's all very well having a very fast instruction, add instruction or multiply instruction. But if it takes 10 times longer to load the value from memory, the speed of memory dominates. And of course, it depends on whether you're loading a byte, a half word, or a word from memory. And you might ask about caching. Well, we have instruction caching starting to appear. In fact, it was on a Japanese research machine in 1962, where they had something like a 64 instruction cache. And so if you have a loop, a tight loop, it would go around in that loop. And so that would run faster because they were caching the instructions. But data caching appeared later in the 60s. And in fact, commercially on the IBM 36085 was the first commercial machine offering data caching, which again is going to affect your performance. You also have complications with the CPU implementation. A lot of the CPUs back then were bit serial. Rather than getting 8 bits at a time or 16 bits at a time, you get 1 bit at a time. So if you're clocking every clock cycle, you'd get a bit. So if you have a 16-bit value, you'd have to wait for 16 clock cycles to get all 16 bits. The advantage of this approach is it simplifies the design of the computer. You don't need as many valves. Turing's ACE computer was a bit serial machine. So he managed to bring down the number of valves to a few thousand valves. Whereas if you look at some of the larger machines, they tend to be parallel machines. So you require more valves, a bigger computer, more expensive computer. But of course, because everything runs in parallel, it runs a lot faster. Also in the 50s and 60s, how do you do an add? How do you add two numbers in binary? What logical circuit should you use? And in fact, Booth at London, I forgot the name of the college, not Imperial, it'll come to me in a minute. The Booth adder was, he came up with a, it's ignoring me, Birkbeck, thank you, yes, Birkbeck. Booth at Birkbeck College designed an adder which a lot of people were using. And so people were figuring out how do you add two numbers, how do you multiply numbers, and so on. They were coming up with more efficient designs. So you might have like for instance, the example here of the UNIVAC 1, it clocked at 2.25 megahertz, but actually an add took a long time. But that was because the adding circuits were sufficiently complicated that it needed lots of cycles to do the add. So there wasn't such a strong correlation between the clock frequency and the instruction timing. So in the 50s and early 60s, we're talking about computers that ran anywhere, the clock cycle anywhere from 50 kilohertz to a few hundred kilohertz. So computers were not yet in the megahertz range. In fact, not until the late 60s, early 70s to be getting to the megahertz range. So this is affecting performance. So here we are, some numbers at last. I hope you can see them. Each of these blue-green dots is a computer. Across the bottom, we have the date. And vertical axis here, we have a number. And you can see it's roughly going from about 10 up to about 10,000. That's a fitted regression line to that data. You can see there's a lot of variability in the performance of the computer. So roughly computers in that time interval between about 53 and 65. This is Knight's data, that short period. They got about 1,000 times faster in that time period. Right? And, yep. Moore's law, Moore's first paper was published actually in 65. So we don't yet have transistors. We're still in the valve. Actually, transistors are starting to appear about here. So we have valves. I don't know if Moore's law really applies to valves because it's transistors on a monolithic silicon. But yes. So about 1,000. So this is one data set that takes us from, actually it takes us from 45, but the quantity of data you need to fit doesn't really kick in till about sort of early 50s. So going from the early 50s to about 65, this is the only large data set covering that period. So there are lots of ifs and buts here and lots of variability, and you can wave your arms around, go, no, I don't believe this, and I don't believe all of it. But anyway, it gives you about a factor of 1,000 over that time period. And so that's a 69% annual growth rate. So they talk about Moore's law today doubling every 3 years. No, in the early 50s, they were doing much better in the early 50s than Intel were doing in the 90s. They put Intel to shame, mate. This is when the growth happened, early 50s, through the 50s and the early 60s. This is when it really took off. And then it slowed down. Hang on, let me get to that. So, so these are Knight's measurements. Now, you might have heard of Grosh's law. Remember Grosh's law? So this was a paper published in 1953 by a guy who was into, I think he was into optics and also, he wasn't into computers anyway. He noticed that this is about the economics of computers, that the economics, the price of computer increased at about the square root of their performance. And this is a quote from the paper. And he as he said, he modestly called this law Grosh's law. And in the 60s and 70s, Grosh's law was widely quoted from this observation made in 1953. And in fact, if you look at Knight's data, up to about the early 60s, it kind of applied. So yes, I was assuming when I came here that people would have heard of Grosh's law, so I thought I'd better mention it. After the early 60s, it didn't apply anymore, but anyway. Okay, so that's calculating performance based on looking at the characteristics of the computer. So now we move on to the other method of measuring computer performance, where we're going to execute some programs. And these are called benchmarks. And to be able to do that, you need a high-level language to be available, because you can't write your benchmark in an assembler for one machine because it won't work on others. And of course, in 1960, we have Algol 60 come out. And you've got to have programs or a program that are representative of user code. Now, the advantage of this approach is it's much less effort needed to produce an answer. You take a program, you run it on machine, it prints out the answer, and that's the answer, that's the performance number. So it's very, assuming you've got the appropriate compiler and it all works. This approach also handles the fact that you've got different instructions. You don't care about that. The compiler handles all of that. And it handles all the issues like cache and all the other features, assuming you've got a representative program. So that's the advantage of doing this. You just send someone a paper tape or some cards, no internet back then, of course, and they run the code and off they go. The disadvantage of this approach is you need a representative program. And I'm going to be I'll say something about how they decided what to do. And the compiler writers would tune their compilers to do well on the benchmark, which as a compiler writer, I mean, why wouldn't you? When I went around talking to potential customers, they say, what are your benchmark numbers? Of course, I have my own company. I'm going to tune my compiler to do well on the benchmark numbers. I didn't do on these benchmarks. I've done it on other benchmarks. I've had compiler writers tell me that they don't tune when I speak to them. Well, why don't you? You should. I've always assumed that if a compiler writer tells you they don't tune for the benchmarks, they're either lying or they're incompetent. And a lot of time, I think they're not lying, they're incompetent. The compiler writers love fiddling with details and doing lots of maths and stuff, and they're not particularly customer facing. I was in a small company, so I was very customer facing. I tuned my compiler to do well on the benchmarks. Why wouldn't you? It's sales, you make money. Two benchmark systems. In the 70s and so on, customers were told that how many COPS, thousands of operations per second. And this was calculated using IBM job mix number 5, which was weighted by doing a sort, a compile, running some commercial apps and then technical apps, and it was weighted by those percentages. And that would give you a number. So that was kind of a mixture of, that is a kind of a benchmark, but it was expressed in thousands of operations per second. There's a wonderful article by Edward Lias in criticizing COPS and saying it's really unreliable. I've got he also gives you lots of data as well, which is nice of him, but then he says the data's rubbish. Okay, fine. And then Whetstone, of course, Whetstone is what everybody used. There are some American reports where they refer to it as the British benchmark. Well, it was British. What's wrong with that? So it was written in 1972, and it was based on some work by Brian Wichmann, who's a member of this group, comes to meetings occasionally. He profiled, got some statistics of Algol 68, Algol 60, running the Whetstone compiler on the KDF9. Sample of 949 programs, so on, so on. And that's how he published the benchmark. Very small benchmark, about 30 odd statements. It's also was converted to Fortran. There's a PL1 version, and obviously there's a C version. Most of the published results are for Fortran. So here's some. So then here's an example. So assign 1.1 to X. This is the time on the Atlas, Manchester MU5, ICL 1900, Radar Research Establishment, Algol 68, and Burroughs machine. That's how long it took that instruction to execute on those machines. And so he's got a whole bunch of the different statements and how long it took to run on different machines. So that's how the Whetstone benchmark originated. These are weighted by multiply, divide, and so on, a representative sample of instructions. So the Whetstone benchmark is actually very, very small, which is perfect for us compiler writers because it makes it dead easy to tune. Because you just find, well, where are the loops and what do the loops do, and just in you go. Of course, back in the early 70s, it was very hard to actually write an optimizing compiler, and very few people did it. So the idea of someone actually going in and doing fancy tuning was sort of in the future still. I didn't get into the compiler business until the 80s, and then we were definitely doing it then. And here are the Whetstone measurements. So again, we've got data across the bottom, and there's the Whetstone number. And this is all thanks to the guy called Roy Longbottom, who was working at the CCTA and carried on doing it. It's sort of like his life's work. He's got a website dedicated to this. He collects all the Whetstone measurements and makes them available. There are 429 Fortran ones, and each one of these dots is one of the Fortran ones. And you can see it going from 1965, actually up into 1995, but it starts to fade out a bit here. And you'll notice we've got, actually this is an increase of about 2,000 or 3,000. But it's over more years, it's over 30 years. The previous one was over 15 years. So we're getting a few thousand increase over twice a longer period. And so we're only getting a 33% annual growth. So the growth rate has slowed down. And the Intel period kicks in about here. We start getting Intel chips. And in fact, although I'm not going to talk about it, if you go from 95 up to the present day, it's got the speed improvement is about 100, so that the growth rate has dropped to about 20%. So the so-called Moore's law Intel is around 20%. Pre-Intel was 30 odd percent, and in the Valve days they were doing 60+%. So all this Intel hype about how wonderful and faster things are going. No. So we've got two sets of measurements. We've got the night measurements. We've got the whetstone measurements. They were done into two completely different ways. How can we join the two together? And so what we need to do, we need to normalize the two data sets. And what we need to do is we need to find computers that ran both benchmarks. So you've got two benchmarks running on the same computer, so you can compare their performance. And the first thing you need to do is normalize the computer names, because when you look at the data, sometimes they use different names for the same computer, so you have to normalize it. And so I normalized it. There's this French guy who has a computer models database with the names of different computers when they came out, and all sorts of information about the computers. I've used the names in that database. And in fact, when I was comparing the names, I discovered about half a dozen different computers that weren't in the database, because I was looking at old computers. And then we've got to fit in the equation that, well, you can map the night numbers to the whetstone numbers. And so if you look at the data, so it's another one of those things with, so 1, 2, 3, 4, 5. There are 5 different computers in the data set that are in the night's data and the whetstone data. And we can fit an equation to those. And those of you who know a bit about statistics will say 5 samples. 5. Well, you know, that's it. And you get this equation here, which you see is a bit nonlinear. Anyway, 5. So there we go. So that's what we do. And then we can put the two together. And here we are. The relative computer performance, 1953 to 1993. So this is the night data in green. The blue is the whetstone data. And this is a piecewise regression. So what it does is it fits over an interval. So we can see about, what is that? What can we get this to? About 1965, see the slope going up, and then it slow. You can see the kink where things slow down. About the mid 60s-ish here, perhaps late 60s, you can see where things start to slow down. And if you say, well, so you've got 53, 80, so we're going from tens of kilohertz to a few megahertz to 100 megahertz, which are kind of the periods of the clock rates, even though the clock rate is not very representative down here. So you're probably looking at 1 million, perhaps 3 million, with some amount of arm waving of the performance difference going from 53 to 93. And we can jump up, I'm very iffy about some of this stuff here. And I wish we had, and the fact we've only got 5 numbers here. Yes, yeah. So this is a somewhat arm wavy. So this bit here, I'm quite confident about the blue stuff. The blue stuff sounds about sensible-ish. This is about, and then we join them together, and the joining together is very arm wavy. So yes, so 1 million with arm waving thrown in is what I would say this is. And if you look at the clock rate, the performance has improved faster than the clock rate. Well, why would that be? Isn't performance all about clock rate? The answer is no. People are designing better CPUs. They're adding caches to CPUs. They're figuring they're doing branch prediction. They're figuring out better ways to do adds and multiplies. they are they're speculating, they're doing instruction speculation. There's all sorts of things you can do on the CPU design to speed up the CPU at the same clock rate. So, but that's happening out here, not down there, or some of it's happening down there. So all the stuff you read in the press about computers being 100 million times faster, it's just not true. You look at the numbers, it's not true. It's at most a million. 53 to 93 is at most a million. Because I think this ought to shrink down a bit, and how you join them together is a bit, yeah. So it's a million. So where next? Well, we ought to remove memory from the calculation, because the amount of memory on the system doesn't really affect performance. It does affect performance a bit, but not a lot. So it would be good to try and reverse engineer out of some of the value, some of the what Knight has done. But really, it'd be great to run Whetstone on much more earlier systems. Now, I know there are people out there who are putting together and running old systems. If you could get a copy of the Fortran or the Algol 60 benchmark and run them on your systems, so we'd have more ways of comparing or mapping Knight's data to the Whetstone data, that would be fantastic. So if you know anybody who's got a really early system, by early systems, I mean pre-1965, and please find people who've got systems that where they have that are in the Knight data, so we can do the Whetstone and the Knight together. Because what we want to do, we want to add more dots in here, so we can get a more accurate mapping from Knight to Whetstone. So I'm doing great here. Where next? And this is a plug for me. My last slide. I'm always on the lookout for software engineering data. So if you have any software engineering data that you can make public, please tell me. I will do a free analysis of your data. I publish all my data on my blog. So if you have any software engineering data, you can share it with me. I'm not interested in source code. I'm interested in human data or very old machine data. You know, repos, project schedules, that kind of stuff. Yeah, please get in contact. So 35 minutes, 10 minutes early. Thank you very much.
Questions?
Yeah, what's the purpose in doing this?
Apart from just analyzing data, because
Yeah.
Just saying. Could you hear the question online?
So the
No,
question
we
was,
couldn't.
what's the purpose of doing this? I got fed up with people just sprouting these in performance numbers and say, well, how do you know this? It's like a meme that someone will quote a number and they'll say 100 million or whatever. So, and the data was there. It's easy to do. OCR it, manually check it. Actually, this the regression analysis is the easy bit. That I can do that in about 10 minutes. The hard bit is collecting the numbers. You're going through and checking, yeah, is the numbers correct? And then fitting the model straightforward, and you talk about it. So it tells you how much faster computers have got. And I'm interested in that figure. How much faster have computers got? So I collect the data, I build models, I try and figure out how things worked, how things used to work. That's my interest, that's what I do.
Okay, if you put your hand up back in the late 60s, the 70s and the 80s, I could have saved all that data for you.
Well, yeah.
The question was, if you put your hand up in the 60s, 70s or 80s, the gentleman would have saved the data for him.
I was benchmark manager in ICL on 1900s and 2900s. I was also a sizing expert on 2900s.
Whenever I read a paper or whatever, I email people, and about a third of the people say, here's the data. A third of the people never reply. And the other third of the people say, it's on my old laptop. Well, in your case, you'd say it's on my old paper tape or whatever.
Yeah.
That,
We were a little more advanced than that, I have to say.
Gentleman at the back.
So if I may cheat slightly, I've got a question and a quibble. The question is, do you see anything in the data that relates to the height that was around? Give me that so people can hear.
Yeah. The question is, do you see anything in your data that points towards something that a lot of hype was made out of, which was the reduced instruction set architecture, and what was effectively its predecessor, I think, which was the CDC scientific computer that adopted somewhat similar techniques rather before all the hype. That's the question. The quibble was about memory. I did a lot of real-time programming in the 1970s in relatively small machines, and in a lot of cases we did things that were limited by memory. If we'd had a lot of memory, we'd have been able to do things by lookup, table lookup. And in fact, we even played tunes on that. We did a mixture of table lookup and algorithmic processing, and we could tune it up and down according to how much spare memory we had. So memory did make a difference in that case.
Oh, yeah.
So that was the quibble, question and a quibble. Thank you.
So the risk in, well, I was writing compilers in the early 60s. So no, actually early 90s. I'm not that old. And so, yeah, I bumped into RISC machines. The idea behind a RISC was about reducing the cost of building a CPU. If your instructions are simple, the design costs, the layout costs of actually building a new CPU was much less than building for a complicated instruction set. And when you do the analysis of what instructions compiler writers generate, compiler writers tend not to use all the complicated instructions, because although the complicated instructions do great things, they don't do it quite right. And a lot of the time, it's much easier to string together some simpler instructions. So the idea was you have a reduced instruction set, which reduces the cost of building a CPU. So you save money on the hardware. And then the compiler engineer would do all sorts of fancy magic to generate instructions that ran just as fast. And for some programs, it worked really well. You had lots of registers, because compiler writers hate it when we don't have enough registers. So store temporary values, you can do some fantastic optimizations. But by then, Intel just had the stranglehold on software and all the RISC chips. I mean, MIPS came out originally. Spark, I did a COBOL code generator for Spark, and the Motorola 88,000, which quickly died to death. I did another code generator for that. Yeah, and the RISC chips were getting more and more complicated. It was kind of interesting. MIPS was really simple. And then by the time that IBM came out with their RISC was actually fairly complicated. They were doing all sorts of weird things. You think, well, hang on, that's not RISC at all. But RISC didn't succeed or didn't take over the world because Intel had that stranglehold on software that runs. So people would hire compiler writers like me because you need compilers first. Then once the compilers are there, then you have to get the application developers to port their applications. And the application developers would say, well, where are the customers who are going to buy our applications? The customers are using Intel. We can sell to them today. Our customer's going to buy your chip, so that then they need our application. And so the application vendors weren't interested. Yeah, Intel just killed everybody off in, yeah, it was death and destruction in the early 90s.
Interesting question and an interesting answer. There's some questions online.
Yeah. So David Holdsworth is asking, do you remember LINPACK? And also, why was the inner product function not a language primitive?
Well,
I'm not sure if that's the same question.
Well, LINPACK is the scientific linear algebra package. Yeah, and of course, the Dongara benchmark as well, which is supercomputer benchmarks. He's been publishing them since the early 90s. So yes, I certainly do. And why wasn't in a product? Well, I think at Fortran, it is in Fortran now. It is a language feature in Fortran, and Fortran is what all the numerical analysis people use. A lot of the scientific stuff is just not used. A lot of code just doesn't use floating point, let alone in a product. If you're not using floating point, well, you know, in a product is kind of a niche within a niche. So that's why you have this division between commercial and scientific applications. They're completely different markets.
But people talk about megaflops.
They talk about megaflops, yes.
So that's floating point.
But the scientific and the engineering people talk about megaflops.
Oh, yeah.
But which is a niche. The business people, where all the money is, talk about flops.
Okay.
Well, in fact, whetstone is a scientific benchmark. The dry stone, which came later, was the integer-only version of whetstone.
I think it's slide 15. That's the one, yeah. It's the RE Algol 68.
It's the Algol, RE Algol 68. There's very high figures there. I mean, the other ones are Atlas MU5 1906. These are computers. This is a compiler. What machine are you actually running that on then? And the figures are very high. Is this because Algol 68 had lots of checking to do? Is this incorporating the checks as well? Why are they so high?
I don't know. I don't know. I don't know what machine. I'm guessing it would be some sort of early ICL machine.
Probably, because I used to run it on a 1905.
So, well, an assignment, there's no checking on the assignment. That's just like,
Yeah.
and it's a bit peculiar because, I mean, is this an optimization? Because you think, well, why is 1 plus m? I guess that's they're doing integer work here. That's floating point. The figures are certainly are very strange.
high,
I guess.
yeah.
Down to the bottom of the screen, there's an interesting line further down.
This is just a snapshot. If you go and look at Brian's, I give the reference to Brian's paper. You can go and look at the.
Burroughs figure is quite fun.
Well, Burroughs was a stack machine.
That
Stack machine.
Oh, yeah. And I had a second question. That was on, I think it was slide 18, I think. That was your, yeah. And I was very surprised by that formula you've got there. I mean, I would have thought whetstone tonight would be roughly linear. And yet, 0.66, that's not much more than square root.
Yeah.
Right, that's very surprising. Why would there be such a difference between a whetstone measure and a light measure?
Well, I think
It's still measuring instruction times.
I think it's the impact of memory, which the
Oh,
gentleman
right,
at the back
you
is
think-
correct. The amount of memory you have can have a significant influence on performance because it decides whether or not you keep things in memory, use table lookup, or you use some complicated algorithm. So that's very algorithm or application specific. I'd assume this was the impact of memory, that the memory is increasing exponentially, and so that's affecting the night data. So that's my assumption here. But with only 5, what can you do with 5?
Yeah.
You're right. I would expect it to be closer to 1, which was why it would be great for other people to run the whetstone on earlier machines to see what's going on here.
And I was quite surprised by slide 11 as well. It was interesting. The graph, that's right. I mean, so I think right to the left-hand side, it's that operations
per second.
I mean, the lowest dot there, what's that, 10 operations a second? Sorry,
Under
that one there?
1945, yes.
Yeah.
Yes. But that's
really
a weighted.
A weighted one, yeah.
Yes, so he's including things like divide, multiply. And don't forget, those early machines, they're only clocking at a few kilohertz.
Yeah, that must be the reason. But then, you've got the best at around about the early 50s. There is when is better than some of the worst ones in 65, 15 years later.
Yeah.
I'm surprised about that.
Well, money. How much money are you going to spend on your computer?
Yeah, I've always thought the technology would have marched on. So
that's true, but there's always a low end of the market, isn't there? Someone who wants
well, that's obviously
simple calculations.
Yeah,
like the CPU in your watch is much simpler than the CPU in a server.
Yeah,
and so I mean, so that's night, but you get the same with the whetstone as well. You've got orders of magnitude difference because you've got expensive computers, you've got cheap computers.
Yeah. Okay, right. Well, thank you very much.
Thank you.
You got one at the back, or were you doing one?
Yes,
online?
question at the back, and then we'll go online.
In 1972, I attended a NATO summit.
Sorry, you need this.
on
You need the microphone.
microcoded machines.
Hold on, hold on.
In 1972, I attended a NATO summer conference on microcoded machines. And we saw the at that time, our view was that a microcoded machine had a low level order code, which was easy to implement, and a higher level order code to keep the compiler writers happy. The interesting bit that came out of it was that IBM was switching almost entirely to microcoded machines, and the reason surprised us. It was that if you had a low-level order code, then the diagnostics of hardware failure were much simpler, and also independent of the level of coding they put above it. And so it was an economic thing on how to improve manufacturing testing, diagnostics, and repairs, which was nothing to do with what we expected.
Well, yeah, I mean, microcode also allows you to fix bugs. If you've got a bug in your instruction, you know, your add doesn't quite work right in certain circumstances or whatever. I mean, Intel are forever releasing updates to the microcode. And the question the gentleman was asking about risk. Of course, internally, the microcode for the Intel chips is essentially a risk architecture. So it's like, you know, complicated over risk. Yeah, and you get people introducing new instruction sets as well. Prime Computer were famous for having umpteen different instruction sets for the same computer, all done via microcode. Well, yeah,
The compiler writers ever happy.
well, we are when we have business. The thing I hate about because Intel compiler writers depend on having lots of CPUs and lots of languages, because then you need lots of compilers, which is great for business. And of course, when Intel wiped everybody out, that wiped out lots of CPUs. So there's a whole lot of business that went away then. And of course, you've got this open source stuff, and where the compilers started out just being good enough, and they got better and better and better. And so that wiped out a different area of business. So commercial compiler writing just died a death in the 90s.
So some more questions online. Mark Woodman's asking if you have anything to say about Moore's so-called law, or on Dennard scaling, or other explanations of the improvements.
Oh, yes. Hello, Mark. He sent me an email saying he unfortunately couldn't make it. So Dennard scaling was a method of, when you fabricate transistors on a microchip, if you scale everything appropriately and you increase the doping density and the width of this, that, and the other, you can increase the number of transistors without increasing the power consumed. And so you can get more and more transistors on a chip consuming the same amount. So the chip doesn't melt. And so when you put more transistors on a chip, you can build more complicated adders and multipliers that work faster. You can put more cache on the chip, and so you can get more cache memory. You can do things like branch prediction. You can do things like pipelining. You can do all sorts of fancy CPU design with all these new transistors, extra transistors, which means your processor goes faster. And the other thing about Dennard scaling is when you reduce the size of the transistors, you can clock them more faster. So Dennard scaling means your clock rate goes up as well. And so Dennard scaling is fantastic for performance. Moore's law is just, actually it's an observation that the number of transistors doubles every 18 months or 2 years, depending on which version of the law you're using. So that's just a consequence of Dennard scaling. Yeah, Dennard scaling is what enabled from 1980s onwards is essentially where all the performance came from. It made that performance possible. You can put more transistors on the chip, you can clock them faster, and their performance goes up. And then when you get to about 2006, Dennard scaling stops. You can't scale anymore. and performance just essentially plateaus. And if you do the analysis, all the performance improvement after about 2010 is because we got faster memory. Faster, all the improvements for spec performance improvements, the CPUs have stayed the same, but memory's got faster. But that's a different talk.
A few people have made comments along the lines that it would be interesting to see data on sort of cost versus performance over the time period.
Yes, in fact, the NICE data includes cost, and I can come back and give another talk on that. Yeah, where they talk about cost per instruction, and you can see that there over the decades there's a slight there's a fit, and you can see the cost. So if you think the cost has come down by roughly 1 million, so you're getting 1 million times faster and you're getting 1 million times cheaper. So we're talking, over 1 billion times improvement in cost per operation. So that's where the big number is, cost per operation, because you're going faster and you're getting cheaper. So the really big number is cost per operation going down.
Brian Russell has got quite a long anecdote on here. Brian, if you can hear me, I don't know if you'd like to unmute and tell us your anecdote. Oh, perhaps not. Well, I'll
yes, I've just unmuted. Yes, can you hear me?
Yes.
Yes, we can.
Yeah, I was at ICL, started in the 1970s, and the acronym MIPS, which most people think stands for millions of instructions per second, we considered was misleading indicator of performance. Because in the 1970s, I was working on P4 as a test programmer, and it had a nominal performance of 2 MIPS. With a clock period of 110 nanoseconds, this meant an average of 4.5 clocks per instruction. That's what we were trying to sell to the customer. But the P4 engineers said, we know all the 1-beat instructions. So they wrote a program that actually measured 9 MIPS. And then the VME programmer said, we know all the very long store-to-store instructions that process long strings of data for only 1 instruction. And they wrote a program that measured 9 KIPS, 1,000th of the KIPS rate. And when the microprogram math library came along, things like square root or sine or cosine tangent, they became a single instruction to call a microcode routine. So although the machine's performance got much better, the MIPS rate, the number of instructions counted by the instruction counter, went down. Yeah. I'm sure this happened on other machines as well.
Yeah. Vendors want to improve their numbers. Yeah, I put my hands up. I tune the compilers. Vendors, in fact, Intel were taken to court for doing things with their benchmarking that wasn't true. And there was that recent case with the phone man. I don't want to name someone. Anyway, a phone manufacturer was taken to court because what they did is they detected when someone was running the benchmark on their phone, and they put their phone into a mode such that the benchmark did very well. They took it out of that mode when they wasn't running the benchmark. And it was a major phone manufacturer, and they got taken to court and fined for it. Yeah, vendors do all sorts of things to improve their benchmark performance.
Volkswagen did something very similar.
Yeah, Volkswagen did something similar, of course. Non-computer world, yes.
Yes.
Hold on. Thank you.
Hold on.
Apropos of
take a microphone.
I remember apropos of your benchmarking, of course, motor manufacturers did the same when they were having emissions tests.
Yeah.
But I was about to add, prompted by the discussion on microcode, this is just an historical note. I was working in a Burroughs shop when they introduced the B1700, which had dynamic microcode, which was tuned to the language that you were implementing on. And it was a very interesting concept, but I didn't stay around long enough to know if it was a commercial success.
Thank you.
Yeah, if you're going to change the microcode by the language, writing compilers is expensive. So what people tend to do is you have an intermediate code that all the languages use. So you'll say half a dozen different languages go to the same intermediate code. And then from that intermediate code, they go out to the different architectures. So if you've got 6 languages, you've got 6 front ends. And if you've got, say, a dozen machines, you've got a dozen back ends. So that's the advantage of going through an intermediate code. Whereas if you were to take every language to every machine, you'd have 6 times 12, you'd need 72 compilers. And so it's a cost issue, that how much are you willing to spend supporting your compilers? And well, of course, I'm going to say this because I'm a compiler writer, but we're put upon, people won't pay what we're worth. So, but it might be a biased point of view.
Just a small comment on that.
We won't be able to hear you, sir.
This wasn't my area at the time, but the CDC Fortran compiler was notorious for that, for basically being built very much one-to-one with no intermediate code, because what they were looking for was scientific performance at all costs.
Cray were fantastic. I've had lots of interesting chats with the Cray compiler people. They spend a lot of time tuning because they have customers willing to pay lots of money to make their code run a lot faster. And when you have customers willing to pay that sort of money, then yes, you pay your compiler writers, and they do a lot of tuning and a lot of analysis as well. The Cray people are some of the few people I've spoken to where they actually measure a lot of customer code because they want to find out what the customers do. Yeah.
Question online.
Yes, Simon points out that inner product is not just the language feature, but has been a dedicated machine instruction on hundreds of millions of games consoles of the last 20 plus years, including Xbox 360. And yeah, there's Al is just saying that even with IBM 360 models that were launched at the same time, there were orders of magnitudes of difference in performance, depending on whether the machines were using microcode or hardwired logic.
Can't hear you at all.
So
Can't hear anything.
the question was the large differences in behavior of IBM machines, but of the time, because of microcode, hard coded this, that, or the other, or snipping the appropriate wires to make them go faster.
Robert has said, and this is actually a question I was going to ask you as well, the green dot for 1945 is interesting. He's guessing it was ENIAC, which would be my guess.
Yes.
My follow-on question was, what was the next dot up as well about 1948? Would that have been Manchester Mark 1 or Baby, perhaps?
Or EDVAC?
Not until 1951.
Oh, okay. So these dots here.
Okay.
I don't know. I didn't. The data's all online. If you go to the GitHub repo of the talks, the CSV files are all there, and it identifies the machine, so you'll be able to see what the machines were.
One in 1945 there. And that am I reading that correctly? It takes 100 seconds to do one operation.
No, that's 10 seconds. 10 seconds.
No, the one right on the left. Right,
oh, this one here. Yes,
that's 10 to the -2.
Well, it's probably. I'm guessing that's the Bell relay computer.
Oh.
Bell Labs relay computer.
100 seconds for one addition.
Well, it's not. It's not. Don't forget, it's weighted. So the multiply and the divide is part of the formula, and it's floating point as well. And floating point on a relay computer is going to. It's faster than human.
A very quick question. Should Drystone have an H in it to match Whetstone?
It should. Have I missed? Have I? Sorry. Yes.
It would in Sanskrit.
Yes. Yeah.
Right at the start.
Oh, right at the start.
DHRI.
Yes. D8. Yeah. Yes, I know. It was probably my spell checker. Got it.
I'm not sure that was a serious
question.
question.
Yes. Yeah. Yes. Yeah. Yeah, there should be DH, there should be an H in there, you're right.
Oh, it was a serious question. Any more questions in the room?
Well, Whetstone's got an H there, so yeah, we'll put a H.
So when I was doing my computing, probably in the 60s, a more important consideration than the benchmarking speed was the mean time between fails on disk units. It was running overnight programs on a 360. More often than not, it would fail. And that was more important to me than how actually fast it would run.
Well, the other thing is the getting your source compiled, of course. Don't forget, people on mainframes in a batch environment, you might only get 1 or 2 compiles a day. I once worked on a compiler where because the developers were only getting 1 compile a day, they would patch the object code because the compiler was producing redundant instructions. They'd figure out where the instructions were redundant and they would patch it, which was how they modify the code. And I was working on an optimizing compiler which produced fantastic code, but of course it didn't have any redundancy for them to patch. So actually, although we produced code that ran faster, the developer productivity went down because they couldn't patch our code because it was so well optimized. There was no redundancy for them, which really surprised. I mean, I guess I can tell you, it's ITT. They spent something like 10 million on this compiler, and the developer productivity. We met the targets of going a lot faster and using less memory, so that this was software going into System X, the exchanges. So we met all the targets, but the developer productivity wasn't a target, and we blew that one out of the water.
We have a couple of questions online.
Yeah, Roland Ibbott has got some thoughts on the relative performance of MU5 and CDC 7600. I don't know, Roland, can you unmute and
Yes.
tell your anecdote?
Yes. We had a visit from some guys from Livermore at Manchester, and they compared MU5 and the CDC 7600. MU5 took about twice as long to run their workload. The 7600 took about 30 times as long to compile it. Because of all the optimization you have to do on the 7600, which is a pig of an instruction set to compile for.
Developers, they want fast compiles and they want to generate optimal code, and you can't do both. The optimal code is going to take a lot of time to do. So yeah.
Well, MU5 wasn't like that. MU5 you could compile quickly and produce quite decent code because the instruction set was designed to be compiler friendly. Yeah. And of course, 2900 followed suit.
All the vendors say that, but yeah, okay.
But we weren't a vendor.
Another couple of thoughts. David Holdsworth saying floating point word lengths an important performance consideration.
Yep.
And Clive is saying IEEE compatibility can slow down floating point quite a bit.
Yeah. Well, at least in the early days, that was one of the complaints about IEEE floating point. It would make things go slow. And of course, IBM had their hex format floating point, which they clung to for years and years and years. And of course, Intel published how the techniques that they were using to make IEEE floating point go faster. And so once they did that, the other vendors came on board. Yeah, there are always the edge cases about how you handle interrupts and exceptions, and yeah.
Well, I think we've got to the end of perhaps the longest series of questions we've had in a recent meeting, which is testimony to how fascinating the talk was. So thank you very much indeed.
Thank you.
End up with a couple of little stories. I was working for IBM in '66, and my first customer was West Sussex County Council, and we just won the council from ICL. Sorry, ICL guys. And there was one reason why they really appreciated the IBM service, and that was because when the ICL engineers changed the printers or changed the rollers in the printers, they wore overalls, whereas our engineer wore a suit and tie and just put plastic gloves on. And then I was told to write a program for the council to perform a demonstration at a local authority conference. And in those days, as you will recall, memory was damned expensive. And I was coding in assembler as I drove down, and I just saved half a byte. And I was 5 miles off my road. Thank you, Roger.
ICT in 66.
You're right, you're right. So, ladies and gentlemen, thank you again for coming. Our next meeting is on April the 16th, when Chris Pick will be celebrating the 75th anniversary of Ferranti Mark I. So I hope we'll see you all again there. Thank you very much.
Well,